Welcome back to part 3 of this chapter. So I have somewhat rearranged the figures that Peter Hoare has chosen to illustrate this chapter by starting with an example taken from proteins. Indeed, the determination of the structure of proteins is one of the principal applications of the Overhauser effect today. Now recall that proteins are large molecules and therefore tumble slowly, and therefore the Overhauser effect is predominated by the W0 transition probability between similar spin states, that is to say the flip-flop rate, and the Overhauser effect leads to a loss in signal. Now proteins, as you know, are basically polymers of amino acids. Each amino acid contains a number of protons, and these protons can be assigned by methods that we shall discuss in chapter 6. Now, since the Overhauser effect is predominantly driven by W0 flip-flop terms, it tends to attenuate signals. So the question really is, if we irradiate selectively a proton that is attached to amino acid number A, could it be that a proton attached to amino acid number D is partly attenuated because of cross-relaxation, because of the Overhauser effect? And if that occurs, we must come to the conclusion that amino acid A must be near in space to amino acid D, because the vehicle that allows the Overhauser effect to occur is related to the dipole-dipole interaction, which, as we have seen, decreases as the sixth power of the distance. So we come to the conclusion that it cannot be a linear chain, but in this case that amino acid A and D must be close in space. Likewise, we can do an experiment where we irradiate a proton belonging to amino acid B, and we find that there is an attenuation of the signal of the proton of amino acid F, and we come to the conclusion that B and F must be close in space, and C and D, etc. In fact, one can typically determine hundreds or even thousands of so-called distance restraints by concluding that certain pairs of amino acids must be close together in space. It is one of the merits of Kurt Wüthrich at ETH Zurich to have shown that if you have a sufficient number of such restraints, you can determine a unique structure, not just one structure that satisfies all these restraints, but there is only one good structure that fulfills all of them at the same time. This is one of the many reasons why Kurt Wüthrich got the Nobel Prize in 2002. Now, although applications to proteins are very important nowadays, we should not forget that we can also use NOEs very fruitfully in discussing stereochemistry in simple molecules. So this is a case where the simple molecule here has been substituted by introducing a trimethylsilane group. And the question that these people ask themselves is whether the silane group was attached here at the top or here at the bottom. And it's not so easy to distinguish these two by any means that is known. Of course, the molecular mass is exactly the same, and many features resemble very much between these two. But if we decide to irradiate the resonances of the methyl groups of the silane, then we see in this case an enhancement of this aromatic proton here and an enhancement of this aromatic proton here. Whereas if we do the same experiment, we saturate the transitions of the methyl group attached to the silane in this isomer, then we would only enhance one aromatic proton. So the answer is very simply, if there are two protons enhanced, we're here. If there's one proton enhanced, we're here. We can confirm this by irradiating this proton here, which stands out in the spectrum. And again, on the isomer on the left-hand side, we would expect an amplification of two aromatic protons, whereas in the isomer on the right-hand side, we would expect an amplification of only one of the aromatic protons. So this is a very convenient way of deciding where the new group has been attached. Now, we don't necessarily have to use Overhauser effect to determine structures and assign resonances. Sometimes it can be useful simply to measure the T1 of carbon-13. And what we have here is adamantane, a famous molecule, and in fact there are two different carbon-13 here. This is on this position here and in this position here. And the obvious difference is that this one has one proton attached to it, whereas this has 2 protons. Consequently, this one is exposed to the fluctuating fields due to the dipolar interaction between itself and the attached proton, whereas this is exposed to more intense fluctuating fields that stem from 2 neighboring protons. Consequently, the relaxation of this carbon is almost twice as fast as the relaxation of this carbon, or if you prefer, the T1 of this carbon is almost twice as short as the T1 of this carbon. So this is a nice, elegant example on how you can use T1 of carbon-13 in order to determine the assignment. So sometimes it's useful to measure both the spin lattice relaxation times, or T1 relaxation times, and the Overhauser advancements on carbon-13. Take this molecule here, where we see that the methine, that is to say the CH carbons, all have T1s on the order of about 2 seconds or so, whereas the quaternary carbons have far longer T1s. The obvious reason is that the protons that are responsible for the fluctuating fields at the sites of these carbons F to I are further away. The reason is obvious, namely that the protons that are responsible for relaxation of these carbons here are further away, since the carbons are quaternary, whereas these have protons that are directly attached to the carbons. We can also see that the Overhauser effects here, which, as you will recall, eta should be at best 2, which is the case here, somehow vary from one situation to another depending on the complexity of the relaxation pattern. For the quaternary, the Overhauser effects are very weak. So in some cases, T1 relaxation allows us to get some rather subtle insight in molecular behavior. This, for example, refers to measurements of the longitudinal relaxation or spin lattice relaxation of carbon-13 in these methyl substituted benzenes. In this case, the methyls are not crowded together, they can't touch each other, they do not interfere with each other, and as you can see, the T1 relaxation time of those carbons is rather long. In this case, however, there is a steric hindrance between the 2 methyl groups. I wouldn't say that they touch each other, but they interfere, and this is sometimes known as a cog-wheel interaction. The idea is that the protons on these 2 groups almost touch each other, although that's perhaps more a view of the mind. Whatever the mechanism is, it is striking that the relaxation becomes much shorter. And clearly, if we plot relaxation times as a function of correlation time, you will recall that there is a curve that goes through a minimum. In this case, we go to shorter T1 relaxation because the correlation time of that cogwheel motion is slowed down compared to the correlation time of the free motion of the unhindered rotating methyl group. There are some more exotic effects which are worth understanding to prevent misinterpretation of many observations. This paper here is concerned with the T1 relaxation of carbon-13 in this rather strange cigar-shaped molecule. If you have a molecule like that, then of course it's much easier to have it rotate around this axis, so the diffusion, the rotational diffusion coefficient around that axis will be much faster than the rotation diffusion coefficient around the perpendicular axis. So there is in this case an anisotropy of the rotational diffusion tensor. In this case, the authors have determined large differences in T1 relaxation times, about 1 second and about 5 seconds, depending if we are in the para or in the ortho and meta positions. And we can explain that if we consider the correlation time, not of the overall tumbling of the molecule, but the correlation time that's relevant for the reorientation of the carbon-proton vectors that either in the para position or in the meta and ortho position. And if we recall this curve, then in fact it turns out that for the para position we have a rather long correlation time. Remember that it takes this slow tumbling here to move that carbon, whereas for the ortho and meta positions we have a shorter correlation time and therefore a longer T1. It is interesting that T1 relaxation of carbon-13 gives us insight not only into the molecular motion but also in the viscosity of the environment, in particular when the molecules are capable of making intermolecular hydrogen bonds. So take this simple case of decane. In fact, there are only 5 distinguishable carbons because of the symmetry, and they turn out to have about equal T1s, and that's not very interesting. But if we go to decanol, that is to say where there's one of the final or the first carbon has an OH group attached to it, then we see a vast range of T1 relaxation times. The C1 carbon, which is really attached to a neighboring carbon through hydrogen bonds, has a very short relaxation time, and as we go down the chain, the relaxation time of the carbons increases. There's also C20, which has a smaller range of relaxation times. Although there are no hydrogen bonds here, the bulk of the molecule is immobilized because of its inertia. Relaxation is not limited to liquids. It can also be studied in solids. And indeed, Raymond Andrew and his co-workers have done this very long time ago in the 50s. Raymond Andrew, who by the way also invented magic angle spinning, which is a remarkable invention, also studied relaxation and line widths in solids at low temperature. And here he studied an ordinary molecule known as benzene and found that if you freeze it, of course, it looks like a crystal or a powder or a glass. But if you're in the temperature range between 200 and 130 or so, the lines are fairly narrow because there is a motion, a rotation around this 6-fold axis in the solid. But if you take the temperature to go below 100 Kelvin or so, you manage to freeze this rotation and you have a true rigid solid, at which point the line width becomes much broader. So we're talking about the proton line width. Likewise, if you look at the T1 relaxation of the protons in benzene, you will find that there is a minimum, and that corresponds to a situation where the rotational motion has about the same frequency as the Lama frequency. Again, these minima can be shifted about depending on the spectrometer that you use for their observation. So far we have talked about longitudinal or spin lattice relaxation, and in this chapter we now speak briefly about transverse relaxation, also known as spin-spin relaxation. The main manifestation of transverse relaxation is that it leads to line broadening. In fact, it's very simple. If that is the dominant reason for the line width, you just measure the line width at half height, and you find that the T2 relaxation time is inversely proportional through this simple relationship. It turns out that the transverse relaxation rate, called R2, which is the inverse of T2, is made up of 2 important contributions. This first contribution we have seen before because that is also responsible for longitudinal relaxation, and it depends on the spectral density at the Lama frequency. But in T2 relaxation there is also a term that corresponds to the spectral density at the origin, at 0 frequency, or the lack of motion if you prefer. You will note that these 2 terms both come with coefficients 1/2. So if these 2 spectral densities are equal, then you can lump them together, but that is only the case in extreme narrowing, when the correlation time is much shorter than the inverse of the Lama frequency. In general, when you go from fast tumbling molecules, remember that 10 to the minus 12 seconds is a picosecond, so that's characteristic for water, then T1 and T2 are equal. And as we have seen before, there is a minimum for T1 and it goes back up again as we go to large molecules. That is not so for T2. As you can see from this graph, T2 inexorably decreases, becomes shorter and shorter and shorter. That means, of course, that the line widths become larger and larger and larger, and that means that, unfortunately, it is impossible to observe proton and carbon and nitrogen signals of very large molecules without doing very smart things. So to summarize chapter 5, we shall look at the points, the bullets that Peter Hoare has put at the end of his chapter. He says nuclear spins attain thermal equilibrium, that is to say the Boltzmann equilibrium, by a process known as spin relaxation. Spin lattice relaxation, also known as longitudinal relaxation, drives the populations of the energy levels back towards equilibrium. Spin-spin relaxation, also known as transverse relaxation, results in NMR line broadening. Spin lattice and spin-spin relaxation times are known as T1 and T2. Spin relaxation is caused by the modulations of interactions between spins due to molecular motions. Dipolar couplings are rendered time-dependent by molecular tumbling, and they are a common source of spin relaxation. Dipolar couplings also cause cross-relaxation, which leads to the nuclear Overhauser effect. T1s and T2s and NOEs give information both on molecular structure and on motion. Thank you for your attention.